G'day, in this video we're going to be looking again at evidence of nucleons and focusing on the discovery of the proton and the neutron. This is our last lesson on inquiry question 2. We've already seen evidence for the existence of electrons and evidence for existence of a dense nucleus in the center, but at this stage no one knows what's in there. This lesson today is all about Chadwick's discovery of the neutron and evidence for the existence of protons and neutrons. James Chadwick's work to discover and identify the neutron was not solely done by himself. The principles of his experiment which allowed him to identify the neutron had actually been done by scientists previously. So we're going to start there by looking at how Chadwick's experiment developed to the point where he actually implemented it. From there, we're going to look at how he used this experimental design and his other methods to be able to identify the neutron itself. And then we'll talk about his contributions to science. So while it's not directly in the syllabus, I think it's important to also talk about the discovery of the proton. In another experiment where Rutherford was playing around with alpha particles and experimenting with nuclear reactions, he fired some alpha particles, a helium nucleus, at some nitrogen. When this happened, the two nuclei combined, forming a heavier substance, oxygen-17. But there was also another product, a single particle, which we now know to be the proton. He observed these particles as radiation, and when experimenting with this radiation to try and discover its identity, he saw that they had the same behavior and characteristics as hydrogen ions. He knew that there was no hydrogen present at the beginning of his reaction, yet there was hydrogen at the end, a smaller particle than the particles he started with. Therefore, the conclusion was that this particle that essentially was a hydrogen ion was fundamental to other types of matter, not just hydrogen itself. Having now identified this particle, he was able to use similar processes to J.J. Thomson to determine the charge-to-mass ratio of the proton. After completing this work, he was able to conclude that this proton that he discovered was much larger than the electron and had much more mass. But when he added up the masses of protons in an atom, let's say a lithium atom with 3 protons, the mass of these protons put together did not lead to the atomic mass of the lithium atom itself. Rutherford's solution to this was to add more mass without compromising the charge. He knew that if lithium had 3 electrons, he needed to have 3 positive charges in excess. So he added pairs of protons and electrons to the nucleus to make up for the mass deficit without changing the charge of the nucleus itself. However, there were 2 big issues with this solution. First off, there was no evidence that the nucleus contained electrons. It was simply a matter of convenience that this would be a solution that could potentially work. And in actuality, it really didn't, because the mass of all the protons and the electrons didn't perfectly match the known atomic mass either. It got it closer, but it didn't account for the mass deficit perfectly. The neutron would be the solution to this issue, but at this stage, it wasn't known. The discovery of the neutron starts with Botha and Becker's experiment. Walter Botha and Herbert Becker experimented with firing alpha particles at elements with low atomic numbers. When they did this with beryllium and bombarded it with alpha particles, they discovered an unidentified radiation. Similar to the previous nuclear reaction, the helium nucleus was adding on to the larger nucleus of beryllium, making an even larger particle. However, there was the release of an additional particle as well. Not only was carbon-12 being made, but also a neutron was being released. Botha and Becker only understood this, though, as some sort of radiation. And when trying to identify it, they had a lot of trouble. The biggest issue being that the radiation had no charge. What that meant was it wasn't being deflected by electric and magnetic fields, and thus they assumed that this new type of radiation was gamma radiation. This was an issue though too, because this unknown radiation had a much higher penetrating power than gamma radiation which had been produced in other nuclear reactions, suggesting maybe that this was a higher energy gamma radiation. At least that's what their conclusion was. Working on trying to identify this radiation, Curie and Joliot modified the experiment and added to it by seeing how the radiation would interact with paraffin wax. Essentially, the wax was able to eject protons. Paraffin was a good source of protons because it contains lots and lots and lots of hydrogen. So if you can knock off one of the hydrogens from the carbon chain, essentially then you have high velocity protons. Because they were able to produce protons off the paraffin wax, it proved that the unknown radiation was not gamma radiation, as photons didn't have enough energy to be able to dislodge the photons from the carbon chain. So at this stage, they were pretty sure that the radiation was some type of matter. Another experiment that they did with the unknown radiation was to radiate a piece of metal in a photoelectric effect setup. And what they noticed was that they couldn't replicate the photoelectric effect with the unknown radiation either, further suggesting that this radiation was not light, as gamma radiation should have had well enough energy to be able to dislodge electrons. So from these experiments, they were able to get closer to the identity of this unknown radiation, the neutron. They knew it wasn't charged, which was correct. They knew it wasn't electromagnetic photons, which was correct. But at this stage, they still just didn't know what it was. So in comes Chadwick in the same year. He looked at this experiment and tried to take just another step further to try and figure out what the particles were. To do this, he measured the velocity of the protons. And by employing some math that focused on the laws of conservation of mass and energy, he was able to work backwards and figure out that from the transfer of momentum from the protons, the mass of this radiation itself. And he figured out that they had pretty much the same mass as a proton. Although, as we've noted before, they weren't exactly the same. This evidence led to Chadwick's conclusion that the unknown radiation was made of matter, it was a particle, its mass was about the same as a proton, yet it had no charge. Therefore meaning that this was a new subatomic particle that had not been discovered before. It was aptly named the neutron due to its neutral charge. This made Chadwick's work quite impressive. Techniques like J.J. Thomson's were impossible in this situation to try and identify the properties of the neutrally charged matter. The genius of his work was that he was able to prove the existence of the neutrons and measure their properties, namely their mass, without directly observing them, instead looking at the behaviour of the protons ejected due to the bombardment of the paraffin wax. As such, the discovery of the neutron solved one of the big issues that existed in Rutherford's planetary model. What was the nucleus composed of? We already knew that there must be protons inside there, but scientists didn't know the identity of the other particles that made up deficits in mass. Fittingly, the mass of the neutrons were able to account for the mass deficit much better than the proton-electron combination that Rutherford had suggested. As a result, we then had our improved planetary model with not just a uniform nucleus, but one composed of protons and neutrons. As such, for a neutral atom, proton and electron count were able to be balanced, and the remaining mass of the neutron could be filled in with our neutrons. This phenomenon was found to work quite consistently across all atoms on the periodic table. However, Rutherford's model still had one glaring issue. How do electrons work? They clearly don't exist by being stationary within the atom. Orbiting doesn't work so well, so how do we solve that? That's going to bring us to the Bohr model of the atom, which we will look at next time. But until then, have a good one.